Hey everybody, WheresWally here. You might remember me from recent classics such as WheresWally and Wolfie measure R twice, ICANN has DITRH bitcoins now please, and Funeral Notice, Year of the Sextant, RIP 2021 to 2021. Well, David Weiss, you asked for proof of a globe, and by that I assume you mean that the Earth is a basic sphere shape.
But how did you get R? Where did R come from? Okay.
Anyway, what follows is a measurement of R, the radius of the globe. I think you'll find this meets your requirements for your challenge for the 3 Bitcoin. And the following proof has been submitted to DITRH and he has conceded that he can't debunk it. Now he wants me to present it to Nathan and the Fed heads. Oh Nathan, I know you'll probably want me to come in on the stream, but I thought I'd let you and the Fed team have a sporting chance. I do love to play with you guys after all. I don't think this will end badly for you. Surely not. So Nathan, just play the next few minutes of the proof. It's much improved from the last time you saw it. And once you've reached the end, I have included a choose your own adventure section where I have pre-recorded responses to the various ways that you will fail to try to debunk me. So there's nothing much more to say than roll VT.
Wally, what on earth do you think you're doing? Stop it.
Oh, sorry mate. So let's have a look. On September 24, 2021, I hired a telescope in Dubbo, Australia. Wolfie was in Sydney also, and he got out his good telescope that night too. We pointed them both at a group of geostationary satellites over the equator, and their GPs are roughly 0 and 109.8666 longitude. Well, both telescopes observed this group of eclipsing satellites in turn as they entered the Earth's shadow, as this was midnight 2 days after the equinox. So these satellites, they reappeared exactly 1 hour, 7 minutes and 34 seconds later. So taking the frame from both uber sextants at exactly the moment when the satellites entered the shadow at 1:58:08 AM local time, I was able to get simultaneous sightings of the same satellite from 2 different locations. Fact A, the 2 uber sextants were measured on Google Maps to be 281.91 kilometers apart. That's not disputable. Fact B, you can see the same grouping of satellites and you can even see the same stars passing behind them, although there is parallax there, obviously. Fact C, taken at the same time as you can see the geosats go dark in both telescopes, so we know that it's the same time. And the timestamps from both telescopes are within a few seconds as well. Fact D, the pointing data from each telescope is given, the azimuths and the alignments are all within 1 degree, so we can pretty much ignore those and treat this as a 2D problem and use Muppet View to explain this proof. Fact E, I used plate solving to verify the telescope pointing angles as well. Plate solving is sort of astronomical almanac, if you will, and it's super cool. The difference between the right ascension values also tell me the angle between the 2 lines of sight is just 0.074 degrees. The 2 elevation values are how far above the horizontal plane the sight lines are. This horizontal is derived from the stars themselves, and it's amazingly accurate, and it matches the local horizontal precisely. I also noticed that the Sydney image was not quite centered on the frame like the Dubbo image was, and by counting pixels I worked out that it was 0.2570 degrees of frame shift, which I corrected for. Now this image here on the screen is only the measured facts, so what does all this mean? Well, I added the difference in the elevations to the frame shift correction and the difference in the right ascension values, and it seems that the level in Dubbo is 2.5979 degrees different to the level in Sydney. If the horizontal planes are not coplanar, then the verticals cannot be parallel, and if they're not parallel, then they might just converge. So the verticals at Dubbo and Sydney are 281.91 kilometers apart at the uber sextants. That is the arc distance, but the chord distance is a mere 23 meters different. So that's good enough for me. It changes nothing. They diverge upwards, so they must be converging downwards. So now we have an isosceles triangle with a base of 281 0.91 kilometers and the acute angle of just 2.5979 degrees. It is simple maths to solve that, just to work out that the two large angles, which are the same and are 88.701 degrees. Now a little bit of law of sines and voila, the length of the two sides of the telescopes to where the verticals converge. Now that we have a point of convergence, you want to buy a vowel? Only costs 3 Bitcoin. So I measured the R as 6218 kilometers or 3684 miles. Now that's just 2.5% from the accepted value. Not bad at all. At one point, Nathan and the Adam Meakin did mention, and little Mitchell too, I think, that maybe I should have used the background stars instead of the geostationary satellite. So as a consolation prize to them for not being able to debunk version 2 of the R-proof, I thought I would add a whole new version 4 of the R-proof, this time using the star called ND218853. Enjoy this R-proof, David. It's not going to cost you an extra 3 Bitcoin. I mean, I'm not going to pull a Mitchell on you. Here we go. R-proof version 4. The Star of R. Bonus round. To keep it super simple, I have used the exact same frames as I did last time. One from each telescope. The Dubbo image was captured on the 24th of the 9th, 2021 at 15:58:08 UTC, and Wolfie's was captured a mere 12 seconds before that. Remember that fact. The first thing I did was to measure in degrees just how far the star was from the center line of the frame in the right ascension axis direction. The target star was close to both images, but I wanted the most accuracy possible. So I adjusted the right ascension according to the values I just calculated here. Next, I realized that because the telescopes were not tracking, the star was moving across the frame. As you can see here, when I superimpose the star from the previous frame, it is quite a bit further to the right 31 seconds earlier. However, I needed to adjust for just 12 seconds of difference. The simplest way to do that is to use the fact that one sidereal day means the star will be back in exactly the same position in the sky. So I simply divided 360 degrees by 86,164 and multiply that by 12 to get 0.0501 degrees of error, which I added to the Dubbo scope as it was 12 seconds behind Wolfie's, which meant the position of the star had moved just 12 seconds too far to the west. That makes the total angular difference of 2.4892 degrees between the two local horizontals at each telescope. So from this point onwards, the method is identical to the previous proof. I now have an isosceles triangle with a base of 281.91 kilometers, and the opposite angle is 2.4982 degrees. Now, when solved geometrically, that inverted triangle has sides of length 6,466 kilometers or 4,018 miles. That figure is slightly longer than the generally accepted average value of R, but now that you can see that I've measured the radius of the Earth, then the fact that there has to be a sphere of radius R, it is so obvious that even a 5th grader could point it out to you, mate. So if you're really struggling to understand just what's going on here with these two horizontals that are now not coplanar, it's quite simple. If you imagine that both sight lines have a very narrow angular separation, which means they're virtually following the same path. So then if you draw the horizontal crossing it at Dubbo, and then go 281 kilometers further along it and draw the horizontal at the elevation angle at Sydney, you'll find it's about 2.4 degrees more acute, which means the horizontal in Sydney is tipping away at about 2.4 degrees. It is that simple, really. So there you have it, the radius of the Earth, measured twice, first time to within 2.5% of the generally accepted average value of R, the second time to less than 1.5%. And this is very close, considering that the Uber sextants were very close to each other. Now imagine how much better this will be when Wolfie and I do it again from opposite sides of Australia, with him in Perth and me in Dubbo. And we are going to do that the very next chance we get. So to help you out here, David, I'm sure you're feeling a little bit faint right about now. Here's my Bitcoin wallet address. Just pop the 3 Bitcoin in there and we're done, mate. Now, there's no need to claim that you don't have my 3 Bitcoin. Mitchell assures us all that you do. Have a listen.
Yeah, DITRH claims to have 3 Bitcoin to give out, but doesn't own 3. So how's he different to Mr. Sensible? Well, DITRH absolutely has 3 Bitcoin. Come on, man. He's very, very open about him being Jewish. He definitely has money. He definitely has 3 Bitcoin, and he wants to give it away to anyone who can give us just 1 flat Earth proof.
Oh, Mitchell, that was more than just a little Freudian, wasn't it? Might have to put that in the sound file. So if you think I've managed to provide a measurement of R, if you think DITRH doesn't have a leg to stand on, if you think the feds have failed, then drop a comment, #PayWally. Nathan, might be time to send an email to David saying you couldn't debunk Wally. Maybe he's got to polish up those 3 Bitcoins and drop them in Wally's wallet. I see that you've chose your own adventure and ended up in the begging the question section. Well, this is a big one. From my understanding of the begging the question fallacy, it's a form of circular reasoning. To be a legitimate begging the question fallacy, I must be stating the final premise in the initial premise. So if the prosecution says, Mr. Oakley, when you killed Owen, did you hide the knife in your hat or in your pants? That's a begging the question fallacy. See how they just slipped in the did you kill part without actually proving it? The way you guys use begging the question, however, is wrong. If I show the Earth curve on the screen in an initial slide, you lot immediately chant begging the question, even though the shape of the baseline has had no part in the proof whatsoever. I know it's impossible for you to refute the facts that have been put before you, and you have to pounce on anything you possibly can. But when you chant begging the question, you're really saying, we don't have a clue, don't like this answer at all, don't like it, get it away from me. You want to claim circular reasoning? Don't just chant it. How about you prove it? I think you'll find I have done none of that in this proof. Well, I guess that obviates that. Seems you've ended up in the Choose Your Own Adventure Black Swan section. Well, Black Swan, really? Is the date the 28th of October 2021? Am I observing this on that day? Am I observing this in the daytime? Am I on Miramar Beach? Am I hot and humid? Well, I'm hot. Am I above water? Am I even in Santa Barbara or California or USA or the Northern Hemisphere for that fact? Am I 1 foot above the water? Is my elevation angle less than 1 degree? No, 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 and 100 times no. None of these things apply. So your cherry-picking black swan is a black swan non sequitur of logical fail. So get out of here before I turn this black swan into layer 4 of the Wolfpack Turducken Christmas jet engine spit roast. I don't think that could even get any more obviated than that. Seems you've ended up in the Choosing Your Own Adventure section, verifying the GPS distance, Dubbo to Sydney. Well, for most people, this would be a simple GPS lat-long exercise. And on Google Maps or Google Earth, you'd use the ruler tool and you'd determine it rather easily. But you know, I've been waiting for you guys to realise a simple fact. And I have been dropping clues too. For you guys who are holding yourselves up as being experts on celestial navigation, you sure don't seem to know much about it, do you? I've even been calling these telescopes uber sextants, for a reason.
Which is your favourite telescope? That one? Is that your one?
Yes.
Wow. Say hello to WheresWally.
Hello.
Do you think that a sextant can be used to measure an angle to a star? And from that angle, do you think it is trivial to get the distance of the telescope location to the GP of the star? Now, you won't find star HD 218853 in the navigational stars of the almanac either, but it's not actually that hard to do the spherical trigonometry that the almanac does for you. Now, you guys would not be able to do it though, I'm sure. You only need the right ascension values and the exact time and date of the calculation to determine the latitude and longitude of the GP of that star at that time. Now, I don't even really need the almanac to get the location of the star's GPs, as all I'm wanting is the difference between Dubbo to the GP and Sydney to the GP. And the GP location cancels out, so all I'm left with is Sydney to Dubbo. So let's have a look at that on my spreadsheet. the two Uber measuring elevations, and I adjusted them a little bit because the star HD 218853 was not in the center of the frame, so I just moved it just a bit to make it in the center of the frame. Now all I do is the calculations for Dubbo to the GP and Sydney to the GP. So simply the corrected elevation angle taken from 90 to get the complementary angle in degrees, multiply that by 60 to get the navigator minutes, or nautical miles actually. The difference in the navigator minutes is 147.31 nautical miles, or 272.89 kilometers. I can legitimately add to that the difference in the two sightlines. They are slightly diverging by 0.074 degrees, which makes 8.22 kilometers difference. Add those two values and we get an estimate of the Sydney to Dubbo distance as 281.11 kilometers. And I measured 281.92 kilometers from Google Maps. That is close enough for me. And I lol that none of you celestial navigation experts realized that you could measure a distance using a sextant. It's such a classic fail. I bet you guys, when you lose your mobile phone, go, "Where's my phone?" And then you pull your phone out of your pocket and say, "I know, I'll ring it and find out where it is." You guys. Obviated yet again. Okay, so seems you're at the choose your own adventure part for how do you get an elevation angle to a geostationary satellite in a sky vacuum? Well, Nathan, it seems like every time you raise an objection to something or other to do with my fantastic R proof, it shows that you really just have almost no understanding of actually what's going on. The technical answer to your question here is I don't need to. Let me explain. Because I'm actually doing two sight lines, whatever correction I'm applying to one is exactly the same correction I'm applying to the other, and because I'm doing a difference between those two, the correction cancels out. Isn't that just lovely? So the correct answer is I don't need to. I think we'll just call that obviated. But let me explain further. Well, Nathan, it's actually super easy. Barely an inconvenience. The Nautical Almanac has, on the inside front cover, a table for altitude adjustments. It seems to be already taken into account. It seems that any angle above 45 degrees of elevation, the correction is less than 1 arc minute anyway. It seems more so that Nathan has never actually even opened a Nautical Almanac. And finally, Nathan, it would appear that you haven't even thought about this question. Any sight line travelling through the atmosphere bends, you've got a bendy hypotenuse. So what are you doing about that, Nathan? If you're having a problem with a curved adjacent, it seems you don't have a problem with your bendy hypotenuse. But of course, that doesn't worry us because we have correction tables for that in the Nautical Almanac. And it seems that a bendy line can actually be used to measure accurately if you know the precise shape of the bend. Ooh, what about that, Nathan? Yeah, that one's so obviated, isn't it? So here you are at the choose your own adventure part for your claim that a satellite is too small to be able to see.
They're sighting it through the telescopes and getting the reflection of these geostationary satellites at 36,000 kilometers away. So I thought, well, how big are they? Do you know what I mean? Because that's really quite far away.
It's only a reflection, mate. It's not being resolved. Oh, and look at this. As they blink back on, one satellite appears to have a large flat area that catches the light and produces a really nice flare.
We don't know. We don't know what the telescope they're using is. They might come back and say, ha ha ha, you said we wouldn't be able to see it. It's too small. Well, actually,
it's too small to resolve, but ha ha ha, we're not claiming we can resolve it. We're saying we can see the light from it. And for that, 1 pixel is enough.
dun dun dun, look at this giant observatory. And now I've got a light in the sky. Therefore, everything I've said is true. Everything you've said is wrong. And I've proved it just because I can show a little dot.
Yep. How does it feel to be debunked by a dot, Nathan? Yeah, I'm going to call that obviated well and truly. Okay, here you find yourself at the choose your own adventure part for your claim that the chord length is not the same as the arc length of 281.91 kilometers.
When you're taking that top of the triangle now with the other 2 points, the other point being at the center of a presupposed spherical Earth, it doesn't match the arc length over the top of it. At chord length, they're deriving that, doesn't give you the same value when you've got the actual arc over the top. Well, that's suddenly missing. It's got a flat top to it, right, Brian?
So I multiply the kilometres by 1,000 to get metres. You got that, Nathan? And this calculator shows the chord is a mere 23 metres shorter than the arc. I guess that's busted the different length argument. I'm going to call that complaint obviated. So once more you find yourself at the choose your own adventure part for the claim that the Al-Bob-A-Runey or whatever that excuse was named. But did you actually check Adam's working? I did, and he was a little bit wrong. What he was trying to calculate is actually only 0.1 degree. And guess what? I measured using the background reference stars 0.074 degrees. Well, that's close enough for me. And guess what? I also allowed for that in my calculations. This is kind of embarrassing for you lot, isn't it? Well, that obviated that nicely.
You get it, Wally.
Well, you seem to find yourself at the choose your own adventure for the Goldilocks fallacy. Now, I'm not sure if this is the right name for it, but this is what I'm calling it, and you can tell me different if you wish. It seems to be a variation on the moving the goalposts fallacy. The tolerances are decreased ever smaller and smaller to ensure that the value is either too big or too small, and it's never just right. Now, this is one that Mitchell from Australia has been committing heaps. He likes to debunk a claim of Earth radius as it's too big or it's too small. Now, I could measure 3957 miles, and Mitchell would go, "Oh, so close, but it's not 3959. You fail, Wally." Oh, and if I did exactly hit it, then Mitchell would say...
Of the R value? So not 3959 miles. What are you getting a percentage error on? Something that has never been calculated, measured, proven?
Seems I can never win, and yet, oddly, I never lose. Sorry about that, Mitchell.
This is not devastating for me at all. Yeah, I was wrong, and I can admit I was wrong. I'll eat a big piece of humble pie.
Shall we call that one obviated? I guess you find yourself at the choose your own adventure for the no 90 degree or flat base required. So the Uber sextant is fully aligned to the heavens. The polar alignment and subsequent plate solving techniques ensure that, and when properly set up, the telescope knows where it is on Earth and what it is in the sky above it. No horizontal planes, no bobble levels, no plates of Mercury, no verticals, no plumb bobs required. The telescope is able to point extremely accurately to any position. The control software has all the ability of the Nautical Almanac, times about 10,000, because it literally has millions of stars in the database, and these stars are updated frequently. In fact, the Uber sextant is so accurate that you can even see the Polaris changing position over the years. Now just check out the reticule that Skywatcher Polar Scope provides for doing a polar alignment, a really accurate polar alignment. There's a little scale on the side there to allow you to pick Polaris in the exact position it will be in different years. It's in different positions. Fancy that. Okay, that's all about how accurate the Uber sextant is. But as Nathan chants here,
measuring an angle to Polaris. Our question, how'd you get that angle? I'll answer.
Precisely.
He needs a flat plane to get it.
how do you get the angle to the celestial object? Well, it's super easy. You barely have to think about it at all. The telescope is measuring the absolute angle of the incoming light ray at the telescope. It does not need a horizontal or a horizon or a vertical. And sure, the elevation angle may be reported as degrees above horizontal, but that does not mean that the angle was measured from horizontal to the star like some cheap dime store sextant. No, the Uber sextant is using the whole sky as its reference. It's way better. Way better than horizontal, way better than vertical. I think I should leave the final note on this issue to Nathan himself. Don't mention 90 degrees.
I mentioned it once, but I think I got away with it all right.
Thanks, Nathan. Thanks, Flatsoid. Thanks, Colin, for bringing this one to me. This is just Own Gold 101. Thanks very much, guys. Obviated yet again.